There are 3 fuel tanks on the Boeing 777, 2 main wing tanks and the center tank. In the refueling process, the main tanks of the aircraft are filled before the center tank. The center tank, depending on the flight requirements, can be empty with some unusable fuel, or having fuel less than the full capacity, or completely filled. There are 78 fuel probes inside the tanks that help calculate the fuel quantity available on the aircraft. The main tanks can carry 31,000 kilograms of fuel each. The center tank carries approximately 83,000 kilograms of fuel, and let's assume the aircraft gross weight is 300,000 kilograms. As the weight of the aircraft acts downwards, the lift produced by the wings adds stress in the wing root areas. Heavier the aircraft, greater is the stress. This wing bending moment can lead to structural failure. The weight of the fuel in the wing tanks helps counter this stress by providing relief from the wing bending moment. To take maximum advantage of the fuel weight in the wing tanks, the aircraft fuel feed system is designed to first use the center tank fuel and then the main tanks. As this decreases the weight of the aircraft and reduces the load on the wings. The weight of the wing tank fuel is still intact and continues to counter the bending stress. Once the center tank is empty, the engine fuel feed system starts using the main tank fuel. But having less fuel in the center tank can create a potential hazardous condition that came to light after the TWA Flight 800 mid-air fuel tank explosion. Let's understand what caused the center tank of the jumbo jet to explode. 3 conditions were necessary for the explosion to take place. First, oxygen in the tank to support combustion. Second, fuel vaporization. Fuel in its liquid form is not flammable, it needs to vaporize before it could ignite. And for the fuel to vaporize, it needs to reach its flash point of 38 degrees Celsius. Temperature in the fuel tank can never reach that level, due to ambient temperature conditions. But the heat generated by the air conditioning packs of the aircraft, located just below the fuel tank, caused the temperature to rise well beyond the flash point. Finally, the spark to ignite the fuel-air mixture. The electrical components in the tank, such as the fuel quantity probes, are designed to work on a very low voltage. This ensures any malfunction of the system does not create a spark inside the tank. But the wiring of the system outside the tank ran alongside other high-voltage system wires. An electrical short between the wires caused a spark that led to the fuel tank explosion. The investigation revealed all commercial aircraft, with a similar design configuration as the 747, are vulnerable to center tank explosion. This led to improvement in wire separation and maintenance standards. Better insulation between the fuel tank and other heat-generating equipments. But most importantly, a new system to be installed on the aircraft. The nitrogen generation system. Any given volume of air is approximately 78% nitrogen, 21% oxygen, and 1% other gases. The NGS uses the left bleed supply to generate nitrogen. The bleed air temperature is significantly high for the system to work. Therefore, the air first enters a heat exchanger, and the aircraft ram air door opens to cool the flow. From the heat exchanger, the flow gets transferred to the air separation unit. The unit separates the flow into 2 parts. Oxygen-enriched air is discharged overboard, and nitrogen-enriched air is transferred to the center tank of the aircraft. The NEA replaces the air within the tank, which vacates through the vent. As more and more nitrogen is pumped into the center tank, the oxygen level inside the tank depletes. The system ensures the level of oxygen in the tank is below 12%. At such low level, the oxygen will not be able to support combustion. And since nitrogen is non-combustible, the nitrogen generation system eliminates the possibility of a fuel tank explosion, even if the fuel vaporizes and electrical sparking does take place. Thanks for watching.